Hello everybody, welcome back to my channel. Today we're gonna take a look at a different machine learning type of paper called Covariance-regularized regression and classification for high dimensional problems. Now, this isn't a typical topic that I would cover in this channel because this has to do more with classical machine learning stuff, or should I say statistical learning. Yeah, I actually don't plan to cover this, but I figure out that it's in one of my PhD group meeting reading. So I figure out why not I share the experience with you guys. Yeah. So okay, just a heads up though, I'm not an expert in this topic per se, though it gets really mathematically involved, which isn't typically my greatest strength. But I figure out why not we learn this paper together. Okay, let's start. So let's go through the summary. We propose covariance regularized regression, a family of methods for prediction in high dimensional settings that uses a shrunken estimate of the inverse covariance matrix of the features to achieve superior prediction. Okay, there's a lot of terms in here. Let's highlight a few of them. Firstly, we have covariance regularized regression. Okay, so it's a new type of regression that uses covariance, I would assume, to regularize the regression method. All right. So, and to say that this type of regression is a family of methods. So it's a collection of methods for predicting stuff in high dimensions. Okay, in high dimensions. I will also assume that predicting in high dimensions that we have taken care of uh, the, the, the curse of dimensionality in some sense, right? So that's my assumption. So we shall see about that soon. Okay, that uses a shrunken estimate of the inverse covariance matrix of the features. Okay, so they use a shrunken estimate. Right. We don't know what a shrunken estimate is, but it could be a type of estimate from what it looks like of the inverse covariance matrix. Now, if you now let's take a look at what is inverse covariance matrix. So let's see what Google has to say. So, inverse of the covariance matrix. It is also called a precision matrix or concentration matrix. Alright, but that isn't say much. So how about we go to ChatGPT and see what it can say. Um, what is it? So let's see. Alright, so that's correct. Okay, a covariance matrix is basically a square matrix giving the covariance between each pair of variables. So it's essentially something like a correlation matrix in that sense. So it provides insights into the variance of each variable and how they vary with one another. So it looks something like this. And I think that's fairly understandable. It looks something like this, right? So the variance, so basically you calculate how they vary accordingly. Yeah. It kind of looks like similar to a dot product in a sense. Well, maybe not, but anyway, right. So what is the inverse covariance matrix? So the inverse covariance matrix is the inverse of the covariance matrix. So basically, it's just the inverse, right? So what's the purpose? So this inverse covariance matrix says how the variables are conditionally independent of each other. Okay, so how not correlated they are, right? So okay, let's write that down. So the inverse covariance matrix, how uncorrelated, um, the, the variables are, right? And this is the opposite of covariance matrix, which says how correlated they are. Okay, so okay, and they say that they use some kind of an estimation of how uncorrelated the variables are of the features to achieve superior prediction accuracy. Just give me 1 second. Can I pause? Okay, sorry for the interruption. Now let's get back to reading. Okay, right. So where was I? Right. So inverse covariance matrix, they use some kind of estimation to estimate the matrix, and they get a superior prediction accuracy. Okay. An estimate of the how uncorrelated the variables are is obtained by maximizing the log likelihood of the data. Okay. So it is done by maximizing the log likelihood of the data. So what is the log likelihood? Let's see. Right. So the log likelihood function is typically used to derive the maximum likelihood estimator of the parameter. And that makes sense, right? So if we take a look into Wikipedia and see what it says, so a likelihood function, well, measures how well a model explains the observed data by calculating the probability of seeing that data under different parameter values of the model. Okay, so it is basically some sort of an evaluation method, right? To see how well it can predict the observed data. So by maximizing the likelihood function, right? Under a multivariate normal model. Okay, so another term right here, a multivariate normal model. Let's have a look into it. Okay, so a multivariate normal model, I would assume, it has to do with something with the multivariate normal distribution, which looks something like this. So if you imagine a Gaussian distribution, but it's more than one dimension, that's what you're gonna get, a multivariate normal distribution. So I would assume that the model is so the model is going to be some Gaussian model in some sense, but we shall see, or maybe I could be wrong. Subject to a penalty, so they use a penalty term. It's kind of similar to deep learning in a sense. Well, let's see. Okay, so it is used to estimate the coefficients for the regression of the response onto the features. What they're saying is that it's training the parameters of the model, right, with response to the to the training data, right, so that they can update their model parameters with respect to the response. The response is Y and the features is X. Okay, and more importantly, right, they show that rich regression, lasso, and elastic net are all special cases of their approach. Okay, this means that covariance regularized regression is a generalized, right? So So let's write it down here. So covariance, so their method is a generalization of rich regression lasso. I think it's called lasso regression and elastic net. Okay, so it's a generalization of existing approaches in regression, and they demonstrate. Okay, right. And they demonstrate that certain previously unexplored forms of covariance-regularized regression can outperform existing methods in a range of situations. Okay, so in right here, what they say is that yeah, yeah. Although this method is a generalization of the existing approaches, right? But since it's a generalization, they can basically invent new subclass of regression approaches. So, and when they do that, they found out that certain unexplored forms of the regression outperforms the rich, the lasso, and the elastic net regression, right, in the set of conditions. So let's see, covariance regularized regression framework is extended to generalized linear models, typically called GLM. All right, so this one is extended to GLMs and linear discriminant analysis (LDA), and they use it to try and predict a real-world data set, gene expression data set with multiple class and survival outcomes. Okay, so there's a whole bunch of terms right here, but I will go through them fairly quickly. So rich regression, if we take a look into rich regression, it is basically, if you know linear regression, uh, it's basically adding in an L2 penalty term right here, and you try to minimize, how do I say, it tries to keep the parameter value small by minimizing this. So that's rich regression. How about lasso? Lasso regression. So lasso regression is basically just L1 regularization. So instead of having the weight squared, you have the absolute value squared. So if you take a look at this beta term here, we are basically trying to do the same thing, right? We are trying to minimize the absolute value of the weights, right? And that should help to regularize it. But there's another one right here that I'm not too familiar with, and this is called elastic net regularization. So elastic net, okay, Wikipedia says it here. So elastic net regularization is a linear combination of the L1 and L2 penalty terms. So let's see what it looks like. All right, so it looks something like this, right? So you add in, so it's a linear combination, essentially. You have lambda 2 and lambda 1, right? Lambda 2 trying to make, okay, so lambda 2, I think it's responsible for weighting the rich regression term, and lambda 1 is responsible for the lasso regression term right here. So that's understandable. So essentially, elastic net is a combination of rich and lasso. So let's see. Okay, and the other term would be generalized linear models, GLM. So GLM is something that I covered before in my studies in statistical learning, but let's have a look at it for a refresher. Okay, So GLMs, generalized linear models, is a class of linear-based regression models developed to handle varying types of error distribution. So it is very useful if the data is not giving you Gaussian behaviors, right? So we take a look into here. So okay, so GLM, generalized linear regression. Okay, it's a generalization of linear regression by allowing the linear model to be related to the response to the y variable with using a link function and allowing the magnitude of the variance of each measurement to be a function of its own predicted value. So what that really means, right? So if we take a look at here, okay, GIM has three components: a particular distribution for modeling, y, the response from among those which are considered exponential families of probability distributions, and the other one, a linear predictor, n equals to x multiplied by the parameter b, and a link function g such that I guess this is the expectation of y given x equals to mu equals to g inverse of g, taking in this I forgot what this thing is called, n. Okay, taking in the linear predictor, and then you get that. Okay, this is quite dense. But what I will say, let's take a look at this one. The link function provides the relationship between the linear predictor and the mean and the average of the distribution function. So it takes the average and it shows you the relationship between the linear predictor and the distribution function. All right, so but let's see what ChatGPT has to say about it. So generalized linear model, explain. So if we do something like that, that's good. So yes, okay, right. So as you can see, there's a few types of link functions. Identity, basically. I see, right. So the link function is like applying some kind of a transformation of the original mean of the distribution. So you can use the link function to transform it into some other kind of distribution, I think. Okay, that's interesting. Let's see. So okay, right. So examples of GRM. Okay, right. So GRM even generalizes logistic regression, as you can see right here. So GRM with binomial distribution and logic link function, blah blah blah. Right. So all of this is great. Let's see if Scikit has GRM. Scikit does not include GRM. Okay, so let's see. Well, that kind of sucks, right? Okay, but that's fine. Okay, let's go through. Okay, right. But anyway, right? Anyway, right. So GLM is a generalization again of many different regression approaches, right? And they say that their covariance regularized regression can be extended to GLM, right? And linear discriminant analysis. So now let's take a look at LDA. So okay, so what is LDA? So to me, LDA is something like a counterpart of PCA, right? But it has some differences, right? So PCA is typically trying to construct the two axes that maximizes the variance such that it better explains the data, while on the other hand, right, the a linear discriminant analysis tries to maximize the component axis such that we can separate out different classes of data. Okay, so I'm not going to go through that in more details, but it seems like, okay, covariance regularized regression can be extended to GRMs and LDA. Okay, so let's write that down. So their method can be extended. Okay, but I got to be frank, I'm not too sure what they mean by extended, right? So, but we shall see soon enough. Okay, let's go through the introduction part. How long is it though? All right, cool. So there's a few things right here. So they have so they start off with an introduction, and then they talk about a specific approach called the scalp method, and then there's subsections, LP penalties, and then provide some kind of toy example here, and then tell you how to maximize some sort of a scalp criteria alongside with LP penalties. And yeah, there's a whole bunch of mathematical description here, and there's some numerical studies here, simulations, if you will. Let's see. So, okay. So there's quite a bit here. Okay, and then they actually talk about classification, right? Okay, so classification. So it's a use case, and then there's more to it. There's the genes. Okay, right. So and I think the gene data is somewhere around here. Okay. So and section 5, they talk about how to extend it to GRMs. There's about Cox model. Okay, funny name. Okay, right. And they talk about the Cox hazard model for survival data. Okay, right. So there's a whole bunch of cases right here, and they have the discussion right here, and acknowledgements and appendix. Okay, right. Let's see how we can approach this. Okay, I tell you what. We will go through the introduction, and after that, we go through the discussion, right? And we shall see whether or not it's worth it to go through the entire paper, because I'm kind of running out of time. But yeah, let's go through the introduction for now. Okay, right. In high-dimensional regression problems, high-dimensional regression problem, where P, the number of features, is nearly as large as or larger than N. So this is the statement that it's referring to, right? P really greater than N, or maybe approximately like N, right? The number of observation, right? So like I say, this has to do with the curse of dimensionality, where the larger where the more features you have compared to the number of observation, the harder it is to like do any kind of like learning at all. So and then talk about how ordinary least square regression does not provide a satisfactory solution. Okay, so a remedy for least squares is to modify the sum of squares criterion that is used to estimate the regression coefficients. by using penalties that are based on the magnitudes of the coefficient. So this is kind of like elastic net in some sense, right? But not quite, as you can see. So okay, here the notation b magnitude of beta power of s is used to indicate this right here. Okay, cool. Many popular regularization methods fall into this framework. For instance, when lambda 2 equals to 0, let's say if this term is equal to 0 and p 1 equals to 0, this basically cancels out and it becomes 1, right? And this one is nothing. Okay, gives the best subset selection. Okay, when that setting gives the best subset selection, not so sure what subset selection means. Okay, P1 equals to 2. If this is equals to 2, it would be regression. But if P1 equals to 1, it gives you thru regression. All right. Okay. So more generally, when lambda 2 equals to 0, but for P1, if it's equal or greater than 0, then this entire equation defines the bridge estimator. Right, so it's a generalized version of the lasso and the ridge regression. So, okay, so equation 1 defines the naive elastic net in the case that P1 equals to 1 and P2 equals to 2, right? So like I say, it's something like elastic net, essentially. So in this work, in this paper, they present a new approach to regularize linear regression that involves a penalty, but not to the sum of square errors, but rather to the log likelihood of the data under a multivariate normal model. So what this is trying to do is to not apply a penalty to the equation, but rather to apply a penalty to the log likelihood of the data under a multivariate normal model. Okay, and I think that's quite an important phrase there, right? So they want to apply a penalty to the log likelihood of the data under a multivariate normal model. And that's what they're trying to do, right? So they don't want to use the same old approach, but we don't really see why, right? They say they want to do this, but why? But why? They will probably say something about it soon, but I guess one thing is that it performs better, right? But we shall see soon enough, I guess. Okay, so right next, the least squares solution is beta hat equals to x transpose x inverse x transpose y. Okay, we know that, right? So that's the solution for the least square regression equation. Okay, in multivariate null theory, the entries of this thing right here, this term, this thing that equals 0 corresponds to the variables, to the pairs of variables that have no sample partial correlation. In other words, right, they are conditionally independent, right? Basically, they are not correlated at all, right? I mean, obviously, right? I mean, if it's equal to 0, that kind of makes sense. But if it's non-zero, that means it is That means it's correlated, right? Corresponds to non-zero partial correlation. All right. So, okay, and then talk about one way to perform regularization of least square regression is to shrink the matrix. So to shrink this matrix, this I would just call it coloration matrix for convenience, right? In fact, this is done by ridge regression, right? Since solution can be written as beta hat ridge equals to that, and that and plus lambda identity inverse xt y. Yeah. So all it did is adding this new term here, which is phi. But okay, so what I would expect is that this matrix right here, something like that, and you plus some kind of a identity matrix for all ones here and all zeros here. So let's see. In fact, this is done by ridge regression, blah, blah, blah. Here we propose a more general approach to shrinkage of the inverse covariance matrix. Our method involves estimating the inverse covariance matrix by maximizing the log likelihood of the data, right, subject to constraint of the elements of the inverse matrix. In doing this, we attempt to distinguish between variables. Okay, so here's the motivation. They want to they want to distinguish the variables that are truly partially correlated with each other and variables that in fact have zero partial correlation, right? So basically the motivation is, right, they want to distinguish variables correlated and not correlated. In that sense, that's their motivation. Okay, so they then use this regularized inverse matrix to obtain regularized regression coefficients. They call this class of method the scout. Yeah, but I'm not so sure what they call it that though. Yeah. So they call their approach the scout, right? So in section 2, they present the scout criteria and explain the method in greater detail. They also discuss the connections between scout and existing regression approaches, and they show that ridge regression and blah blah are special cases of scout. So their entire approach, right? They should call it scout. Scout. So it should have been written like this: scout a, yeah, scout a covariance blah blah blah. They should have done that for the sake of clarity. In addition, we present some specific members, right? So they have some new methods, right, that can be derived from the general formula, right, that perform well relatively to existing approaches. When they say perform well relatively, I would say they perform similar in some sense, but not like a big improvement. But yeah, we shall see when we get to the results. So in sections 3, 4, 5, we demonstrate the use of these approaches in regression, classification, GRM settings on simulated and on some gene expression datasets. Guys, you know, the thing that I really don't like about this type of paper is that the evaluation that they performed, right, for their approaches are really simplistic, right? Unlike the usual deep learning papers where we have to evaluate it on so many large data sets, all they have to do is to get some simulated data and a couple of gene expression data and call it a day. I mean, right, there are some major cultural differences from what I can already tell, and I honestly don't really admire this kind of culture, right? But regardless, though, yeah, let's actually go to the discussion and see if it's worth it or not to even cover their approach. So, discussion. We have presented covariance regularized regression, basically scout that presents a scout that is obtained by estimating the inverse covariance matrix of the data by maximizing the likelihood. They show that the rich, lasso, and elastic net regression belongs to scout essentially. In addition, they explored some new methods from Scout. They have extended Scout to classification and GLM, and they have demonstrated the performance. Demonstrated what performance? Is it good or not? Right? They don't really say it here. Okay, right. Okay, right. Now this is interesting right here. Okay, so they talk about the drawback of their approach. So uh, the problem with Scout is that when P1 equals to 1, right, and the number of features is large, maximizing the first Scout criteria can be slow. Okay, so there is some heavy computational cost right here. When more than a few thousand features are present, the Scout with P1 equals to 1 is not a viable option, right? So it's not efficient in that sense. You can just say that out loud. However, Scout with P1 equals to 2 is very fast, right? So, okay, right, and we are confident that computational improvements will lead to increases. Basically, it's a future work, right? So this is future, I would say, not necessarily covered in this paper, right? But I would also say that maybe this isn't exactly future because this paper is actually kind of like a long time ago, back in 2009. So yeah, okay. It probably has been solved by then. But anyway, let's continue. Roughly speaking, the method in this paper consists of two steps. Okay, so they have a summary, right? The features X are used to obtain a regularized estimate of the inverse covariance matrix. This can be thought of as pre-processing the features, which is standard. You use the features to get a regularized estimate of the inverse matrix. Okay, right. And next, the pre-processed features are combined with the outcome y to produce an estimated regression coefficient. Basically, you just use the pre-processed features and the y label to get your model parameters. And this is in the language of deep learning, right? Okay, in the first step, the features are pre-processed without using y. Indeed, many pre-processed without that, blah, blah. Principal component regression is something like that. Right. It has been shown that for lasso to have this kind of model selection consistency, right, and certain conditions for the feature matrix must be satisfied. Not so sure what these conditions are, but anyway, a review. Okay, right. So I assume it has undergone peer review. A reviewer said, asked whether the scout can offer a remedy in situations whether these conditions are not satisfied. This is an interesting question, but it's future work. So, covariance-regularized offers a way to understand existing regularization approaches, right? So, okay, from what I can tell, this is just basically a paper about how to generalize the existing approaches and come up with different new approaches, but the new approaches doesn't necessarily performs better than the existing approaches, which is half useful. And what I mean by half is that it gives you a new insight, but it doesn't necessarily guarantee you that you can achieve higher accuracy with Scout. So, okay. And since that's the case, I don't think we should even bother covering the entire paper, honestly. So, how about if we just get to like the main part of it? Let's see. Let me see a second here. So okay, right. This is the data. Let's have a look at it. So some kind of a simulation. Let's see. Right. So if we compare it, simulation 1, 2, 3, 4, 5, 6. So let's compare the results. I will assume that the lower it is, the better it is. So there's 6 replicates of the simulation, I think. So if we compare it, if we compare ElasticNet, right, it's that, and this one's that, right, but this one's higher, and this one is higher, and this one is higher. Okay, right. Yeah. So Scout 1 and Scout 1.1 and Scout 2.1 seems to perform better in this simulation experiment. And let's take a look at this one right here. That's the median L2 distance, but let's take a look at MSE, mean square error. So, okay, this one is higher. No, actually, this one is higher. This one is higher. This one is higher. These two are higher. This one's higher. And this one is higher. Yeah, I guess Scout works better for the simulation. But what about some? Yep. Okay, so we got some genome data set here. Let's take a look at it, shall we? So let's see. Okay, cross validation error. It gets 22. That's the lowest one, and this one 11. Yep, that's on par with this. And the number of genes used. Okay, right. That's not that important, I think. Okay, if we compare the test error, 7. Okay, right. So it scores 7. Right. Not so sure what the units are. Pretty sure it's described in the paper. But yeah. Okay, and there's more data sets here. Lymphoma, another biology data set. But let's go through it. Yeah. Okay, so the results basically says that the Scout approach is better, right? But okay, for the sake of time, since I will be in the group reading, we will be covering the entire paper, so I wouldn't want to cover everything since I'm gonna be doing that in a couple of hours later. How about if we just go through some parts of their approach, right? So let's go through Scout first. Okay, So the scout method. Okay, so let's start off by defining the matrix of the data, n by p matrix, right? Where n is the observation and p is the number of features. So come on, highlight. Yeah. Let y be the response value for each observation. So it's something like that. This is basically it, right? So you got some entries, and this is n, this is d, and this is 1, right? So okay, assume the columns are standardized and y is centered. We can create a matrix x tilde equals to that, where it's just this, right? So you basically concatenate them together. If we assume that this follows some kind of a normal distribution, then we can find the maximum likelihood blah, 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 by maximizing this term right here, where s equals to this term. So okay, let's see. So blah 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 blah. Theta, right? Let theta be a symmetric estimate of the inverse covariance matrix. Okay, so the problem of regressing y onto x is closely related to the problem of estimating the inverse covariance matrix. So it's basically kind of similar, or it's kind of equivalent in the sense. Okay, so if p is greater than n, if the number of features is greater than the number of observations, some type of regularization is needed. So you need regularization since S is not immutable. Right. Even if the number of observations is greater than the number of features, you may still want to shrink it in some way to achieve. That means you want to regularize it too, even though if your number of observations is large, is what they say. And the connection between estimation of theta and estimation of least squares coefficient suggests the possibility of, rather than shrinking the coefficients b by applying a penalty to the sum of square errors, right, we can obtain a shrunken beta estimate through maximization of penalized likelihood of the data. Oh yeah. Okay, now that I think about it, right, can we apply this to trading neural nets, right? Because if you think about it, right, the lasso, we already have L1 and L2 regularization, right, which you can implement using PyTorch. So can we try to apply Scout for regularizing, right? For regularizing neural nets, and I think this is some kind of approach that can come out from this paper, right? If any one of you guys know if there's any work related to this, please let me know. Right, but let's continue. All right, so to do this, they could estimate this inverse covariance matrix as theta that maximizes this equation, this term right here, where j theta is the penalty function, blah blah. This j denotes the sum of absolute values of elements if p equals to 1, and it denotes the sum of square errors of theta if p equals to 2. Okay. The regression coefficients would then be given by this formula. However, recall that the ij element of theta is 0 if and only if the partial correlation of xi and xj is 0. Okay. Note that y is included in x tilde, so it does not make sense to regularize theta as presented above, since they only care about the partial correlations, right, from each of the feature variables instead with the y label, right? We don't care about the correlations given the response, but only between the x values, right? So, and for that, they have to do some kind of an adjustment. So they propose a two-step maximization approach, right? So firstly, you compute theta hat xx, right? And after that, you compute theta hat, where the top left P by P sub matrix is constrained to equal to theta hat xx, the solution to step 1, and after that, right, step 3, you compute beta hat given this, and then step 4, you compute beta hat star given the coefficient multiplied by beta hat from step 3. So this beta hat star is the regularized coefficient that you obtain by using the scalp approach. So okay, right. By penalizing, we are attempting to distinguish between pairs of variables that are truly conditional dependent. They are correlated, and pairs of variables that appear to be conditionally dependent because of chance. Right? We are searching or scouting. Okay, that's the motivation behind the name, for variables that are truly correlated with each other and conditional with other variables, right? Not because of chance. Our hope is that sets of variables that are truly conditional dependent will also, okay, so their assumption is that the set of variables that conditionally depend on each other will also be related to the y label, right? So in the context of a microarray experiments, we are now talking about real world cases where the variables are the genes and the response is some clinical outcome. The assumption is that they want to look for genes that are part of the pathway that related to the response, and expect that such genes will be conditionally dependent. In step 2, they shrink their estimates of the partial correlation between each predictor and the response, given the shrunken partial correlations between predictors that we estimated in step 1, in contrast to OLS, ordinary least square regression, which uses inverse of the empirical covariance matrix to compute regression coefficients. We jointly model the relationship that P predictors have with each other and with the response to obtain the shrunken coefficients. All right. So as you can see, right, there's a lot more details, right? So I say, if I look at how much time I've spent, all right, it's almost an hour. But let's go through the final paragraph together. We define the scout family of estimated coefficients for the regression of y onto x as the solutions b hat star that are obtained in step 4 in the scout procedure. We refer to the penalized likelihoods in step 1 and 2 of the scout method as the second scout criterion. So for the rest of the paper, they will be covering how to do this exactly, right? And for step 4, they ignore the C term for brevity. So the C term is where is the C term? Okay, right. So they will ignore this. So you won't be seeing the C term after this part. If we claim that to you, and that, okay, blah, 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 blah. All right. So, okay. There's obviously a lot more parts to this paper, right? But I would like to invite you to check it out for yourself if you are interested. But that's it for now, and I hope you guys enjoy the video. Please do make sure to like and subscribe and leave any comments down there, and maybe we can have a discussion about this paper and how it might contribute to its deep learning, right? Because although this is a simple machine learning, I wouldn't call it simple, right? It's a classical machine learning field, but it does offer some unique approaches in which we can also apply it in deep learning, and maybe it could be a part to achieving AGI. Who knows? But anyway, if you like what you saw, like and subscribe, comment, and I'll see you all in the next video. Bye.